This is lesson 3.3, concavity and second derivative test. Today, what we're going to do is talk about how the second derivative relates to concavity. Concavity is the curvature of a function. So whenever we say something's concave up, it has this kind of shape, kind of like a quadratic opening upwards. Whereas concave down looks like a parabolic opening downwards. And with most curves, what you can do is use pieces of this or parts of these and combine them to make one curve or a couple curves or a couple functions that you have. So some more definitions that we need to look at. So look at this function, f of x equals x cubed. We've seen this function before. Nice S-shaped curve that seems to just lie flat at one point. Well, we're going to find when f prime of x is equal to 0 and f double prime of x equals 0. So first off, f prime of x, in this case, would be 3x squared. As we saw before, you can look at values before and after to tell whether or not we have a increasing, decreasing function and where we can have maximums and minimums. Well, in this case, you'll notice that the slopes before 0 are positive and the slopes after 0 are also positive, meaning that this spot right here is neither a maximum nor a minimum. Which just turns out to be x equals 0. So, if we look at where the second derivative, let's first find that, which is 6x, where that's equal to 0, we get the same location. But right there you can see the curvature. This is concave down beforehand and concave up afterwards. So not only does the first derivative test not completely tell us a whole lot here, still doesn't tell us that we have maximum or minimum because it only goes from positive to negative or negative to positive. But now, if we look at our second derivative right here and find out where it changes from positive to negative, you'll see that before, the values for the concavity are negative, and afterwards, positive. So now we can use second derivative values to determine concavity. Okay, so moving along. So as we saw, again, slopes before are positive, slopes after are also positive. However, for our function, let me write these functions here. So f prime of x was 3x squared, and f double prime of x was 6x. So no matter what value you put in for x, it's going to be positive, multiplied by 3, it's still positive. However, if you put negative values in the second derivative, it's going to be negative. And if you put positive values in for x into the second derivative, it turns out to be positive. So it tells you that this function is increasing in both locations, but beforehand it's concave down. You gotta find a faster way to write this. And afterwards is concave up. We'll talk about how to write this a little quicker later. Okay, so this point where the function changes from concave up to concave down, or vice versa, is called a point of inflection. And because it has such interesting properties, this is another critical number. Okay, so we come up with a second derivative test based on this. So let f of x be a differentiable function and c be a critical number. So if f prime of c equals 0, and f double prime of c is greater than 0, then we get a local maximum. Sorry, local minimum. Meaning if it's opening upwards, but at that spot, its slope is 0, then we got a local minimum. If f double prime of c is, if f prime of c is equal to 0, and f double prime of c is less than 0, then we get a local maximum at that spot. These are the key parts of this. The third part, if f double prime of c is equal to 0, doesn't necessarily mean f prime of c is equal to 0. F prime double prime of x changes signs at x equals c. Then f of x has a point of inflection at x equals c. So this is the second part of the second derivative test. That tells you where you get intervals that are going to give us intervals of concavity, or changing from concave up to concave down, or vice versa. Okay, so determine the intervals of concavity and points of inflection for your function right here. Use this to sketch the function. Okay, so first off, we're going to find out f prime of x. That's negative 4x cubed plus 36x squared minus 60x. Wow, some big numbers. Okay. To find our points of a concavity, or points of inflection, we need our second derivative. Okay, so now second derivative is negative 12x squared plus 72x minus 60. You'll notice that all these values are divisible by 12. So I'm going to factor. I'm going to factor out negative 12. So x squared minus 6x plus 5. If this was not fully factorable, we could use quadratic formula, but thankfully it is. So there's my second derivative. Where is it equal to 0? At the values of 1 and 5. So these values of 1 and 5 are probably points of inflection. We just need to verify that they're points of inflection. So we need to actually find out what the slope is before and what the slope is after. So again, I'm going to create an interval chart. Okay, I have x values lower than 1, I have x values between 1 and 5, and I have x values greater than 5. I'm going to be testing it for f double prime of x, which will give me f of x. Notice that we're not looking at the first derivative here, because we're not interested in intervals of increase and decrease. They're just intervals of concavity. So our second derivative is a parabola opening downwards with zeros at 1 and 5. So that means it's going to be negative here, positive here, and negative here. So I'm going to say this is concave down. That easier? Concave down, CD. And concave up here. And concave down here. So it does switch from concave up to concave down. So we do have our intervals of concavity now. So let's find our points of inflection. So that means I've got to substitute the values 1 into our original function and 5. calculator to do so. Work that out. So this is at -8, and this one's at 136. Okay, so here we have some points of inflection. So let me write a therefore statement right here, and then we can draw a sketch of what this looks like. So f of x is concave up when x is between 1 and 5, concave down when x is less than 1, or x is greater than 5, and has points of inflection at 1, -8, and 5 and 136. Alright, so let's draw a little sketch of what this looks like. So it looks like we're only in the positive x values, but we're having negative and positive y values. Okay, so y, x, 1 and -8, so 1 and -8. Let's say 1 and -8 is down here. 5 and 136, 5 and 136 way up here, let's say. You know, this is a the original function is a quartic, opening downwards. Ooh. Okay, but we know it's concave down at before 1, so we got to draw some kind of function that's concave down here. So let's start with something like this, maybe. That's a concave down feature. From 1 to 5, we know it's concave up. So between 1 and 5, some kind of concave up feature, like this. And then from 5 and on, it has to be some kind of concave down feature. Something like that. And there we have a sketch of what f of x might look like. Okay, moving right on. Use a second derivative test to determine where f of x has a local minimum. Okay, so first we got to find our first derivative. So first derivative of this one is 3x squared minus 6x. And because we're looking for local minimums, we're looking for when this is equal to 0. So 3x squared minus 6x. We have to set that equal to 0. I can common factor out of 3x. I'm left with x minus 2. So we have either x equals to 0 or x equals 2. So one of these two values is where it is a local minimum. Well, in order to find that out, using the second derivative test, I need my second derivative. So my second derivative is 6x minus 6. Okay, I'm going to substitute 0 in for this. That's the value of -6, and substitute 2 in. That's positive 6. So right here I see it's concave up. Here I see it's concave down. Well, in order to for it to be a minimum, it's got to be concave up. So this location, this value of x, must be where we have a local minimum. It just says where, so we don't actually have to find the point unless you'd like to. So maybe we'll find a point. So we'll actually substitute 2 in to the original function. I'll grab my calculator this time, work it out on the calculator. So according to my calculator, I get a value of -2. So therefore, at 2 and -2, we have a local minimum. Oh, sorry. I spelled minimum wrong. Minimum. And there we go. And thus concludes our lesson.